So after determining the probability, again, how likely is it for an event to occur? One of the things we need to do is determine if that probability actually matches real life. And that is why we have to use what's called the chi-square test. So the chi-square test is stats, right? This is statistics. So if you have taken a statistics class, you're probably feeling pretty confident right now. If you haven't, don't worry. I'm going to give you what you need to get through, I promise. So we are going to go kind of step by step on how to use the chi-square test, and then you're going to be taking data from the lab and actually applying it and seeing how the statistics kind of wrap up. Can we confirm or deny our hypothesis, which is really what our chi-square can do for us. We're going to be comparing observed numbers, the actual data that would happen in the real world, versus the expected data, which is the probability. This is our hypothesis. So the expected data is our hypothesis. So in your lab book, you're going to see an example. So you can walk through this, or I'm going to walk through it a little bit as well so that you get an example. Also remember that there are examples in the YouTube channel that go through different examples so you can see the math and how to do that. So the example in your lab book is looking at a bag of marbles. Okay, so you have a bag of 1,000 marbles, and that bag of marbles is supposed to be 60% white marbles, 40% blue marbles, and you need to count them and to figure out if that percentage is actually correct. Now, unless you have way too much time on your hands, you're probably not going to sit down and count 10,000 marbles, right? So you're going to take a percentage of those marbles and count them. So you are going to count 100 marbles, okay, just 100. And you are going to see if it follows the 60 to 40% rule that it's supposed to. And so when you count your marbles, you put them in this cute little table that we have for you in the lab book, looking at the observed number. How many white marbles do you find? How many blue marbles do you find? So when you counted, you had 66 white and 34 blue. Cool. Is that close enough to 60% and 40%? That's the question, right? Some of you are like, that's definitely not close. 66 is not the same as 60. And others of you are kind of like, well, that's close enough, isn't it? This is why we have math. Math is going to help give us a very concrete, yes, we can support that this is following what we want it to, or no, we reject it and it's not. So that's what our chi-square is really for, comparing our observed to what we expect and seeing how close it is, right? How can we follow this? So you're going to follow this table. So the first thing we need to do is figure out our expected value. Okay, so if we have 100 marbles, our expected value should be proportional to our probability, right? So we counted 100 marbles. So in order to figure out your expected value, you're going to multiply times your probability. Now our probability here was 60% should be white, 40% should be blue. So you're going to take the total of 100 and multiply it times the probability of white, which was 60% or 0.6, to get your expected for white. Then you are going to multiply 100, again the total, times the probability of blue, which is 40%, and that's where you will put that here. So that one, this one's pretty easy. 100 times 0.6, 100 times 0.4 gives you 60 and 40. Now I will tell you right here you should stop, and you should double check your math. Add this up so that you get the totals here. The total of your observed should be exactly equal to the number of your expected. And if you do get decimals here, you should leave them here. I know you probably don't get half of a marble, but it's still an expected value. So we should leave our decimals here as well, but that should still give you an equal number here. Now from here, you're going to do the math. So you see in your lab book that, you kind of have the math at the top of your table. So O minus E is going to be 66 minus 60 and 34 minus 40. So you will get a negative number here. Please leave the negative number here. So you have a 6 and a negative 6. Now, again, this is another place to stop and check your math. If you add this column straight down, you should get a 0. It's a great way to double check your math. If you don't get a 0, something went off, right? So go back and double check. Now you are going to take this O minus E and you're going to square it. So 6 squared and negative 6 squared. So this will give you a value. Now then you're going to take this value and you're going to divide it by E, which is your expected. So 36 divided by 60 will give you this value, and 36 divided by 40 will give you this value, which will give you a 0.6 and a 0.9. Now this value, you are going to then add straight down. Okay, so you're going to add 0.6 and 0.9, and this is going to give you what we call our chi-square value. This is your calculated chi-square value. Now the calculated chi-square value is what we're going to use to actually confirm or deny our hypothesis. So again, our hypothesis here is that it should be 60% and 40%. There should be 60 whites and 40 blues if we count 100. Now what we're finding is that our chi-square value is 1.5. So what does that mean? Now there are known values for this. So there is a table in your lab book that is a shortened, condensed version of a gigantic table. If you've ever taken statistics, you've seen this table. It's huge. We've made it a little bit more condensed for our purposes. So we need to know how to use this table. So this is the table from your lab 10, table 10.1. Even though it says 11.1 on the picture, it used to be lab 11. Anyway, I apparently didn't catch that. So to use this table, it doesn't matter what figure number it is, you are going to first find what is called the degrees of freedom. So for our purposes, the degrees of freedom is going to be the number of outcomes minus 1, and that is going to give us the n value on this table. So you notice here we go n 1 through 5. Obviously this can be much higher, but we are not going higher than 5 in this lab. So for this lab, for this experiment, this example that I just did for you, blue versus white marbles, we had 2 outcomes. It was either white or blue. And we subtract 1, which means 2 minus 1 gives us an n of 1. So we are only going to be looking at n1 row, right? We're going to look at the top row for this example. Then what we need to do is figure out how confident do we need to be in our data in order to support this. Now again, if you've taken statistics, you've used this table, you can talk about how, I am 90% confident in my data. We don't really care right now how confident we are. We only need to know how I say if we support our hypothesis or if we reject our hypothesis. Now, the trend for our chi-square value is the lower the number, the more accepted it is. The higher the number, the less expected it is. But what's our threshold here, right? How accepted are we going to be? So, lucky for you, there's a chi-square magic number for that. It is called our critical chi-square value. So, in order for us to accept our data, we have to fall smaller than, lower than the 0.05 column on this table. So, this is what we call our critical chi-square value. So, if we are to the left of this, if we are in a smaller number than is what is on 0.05, then we will accept our data. And if we are to the right of this or larger than this number, then we will reject our hypothesis here. So our critical chi-square value will be found in the 0.05 column. If we are higher than that value that's there, we will reject it. If we are lower than that number, then we will support it. Okay, so let's look at our example. So the example of our marbles, 0.15 was our calculated chi-square value. Now we're going to compare that to this table. So where do we need to look? First, you need to find your degrees of freedom. We did that earlier. It's 1, right? We had 2 outcomes, blue and white marbles. 2 outcomes minus 1 equals 1. So we're going to be looking at the n1 column. Now then also remember that our critical chi-square is the value that is in the 0.05 row. I guess that's the column, not the row. That's the column. It's 0.1 row, 0.05 column. So the critical chi-square value in this, for this specific experiment, is 3.841. Okay, so 3.841 is our magic number. If we are below that number, then we support our hypothesis. If we are higher than that number, then we reject our hypothesis. So you'll see this in your lab book, right? If our calculated chi-square value is less than that in the table, which is our critical value, then it is supported. If it's more than, then it will be falsified. So if we are 3.841, we are supported. If we are at 3.842, we are rejected. So we just have to hit that number. So in the lab, you are going to be looking at different experiments and figuring out if your observed value is close enough to your expected. So in this case, our hypothesis was supported. 60% of the marbles are white, 40% are blue. We support our hypothesis. And that's all we need to say. We don't need to say how confident we are. So as you go through the experiments for this lab, remember 10.1 was you flipping some coins to get some data. You're going to solve the chi-square for that. Was your coin flipping 50-50? Then you are going to move into experiment 10.2, where you're going to take the class data from those coin flips and add everyone's together. So again, remember your probability for heads is 50%, tails is also 50%. So you're going to take the observed value from your class and you're going to calculate the expected based upon your total. All right, so remember your expected is based upon the total at 50%. Now the experiment 10.3, you are going to take 2 coins and flip them at the same time. Now here your probability will change because you are doing 2 things at the same time. So remember, if you want to flip a heads and a heads, that is 0.5 times 0.5, which is 0.25. So your probability of 2 heads is 25%, then heads and tails is 50%, and 2 tails is 25%. This expected value is based on 100 because you're going to do this 100 times. And then you're going to take the whole class for experiment 10.4 and you're going to do the same thing. Again, you are going to be totaling everything from the whole class, and do note that this number will be higher than 100. It'll probably be 600 to 800 depending on how many groups are in your class. So this number will go up, which means these numbers will go up because it's 25% of your total, 50% of your total, and then 25% of your total, which then should give you, 600 to 800 coin flips here. Now note that you're going to be comparing experiment 10.3 and 10.4. 10.3 is your data. 10.4 is your class data. Remember, the more data you have, you should have a more accurate experiment, which means your chi-square should get lower. But notice the hypothesis doesn't change, right? Our hypothesis is the probability. It's still 0.25, 0.5, and 0.25. It's just that you will have more data, which means hopefully you will become more accurate. So remember, the closer you get to 0, the more accurate you are. The more data you have, the closer you should get to 0. And if you ever hit 0, perfect right on the head, then you should go play the lottery because you got really lucky. You had a perfect experiment. The observed matched the expected perfectly. Now for the next couple of experiments, 10.5, 10.6, and 10.7, what you are going to be dealing with is a 3-to-1 ratio. This is not a 50-50 split. This is based upon heterozygotes mating, both 10.5, 10.6, and 10.7. You will have a 3-to-1 ratio, which means 75% will have the dominant phenotype and 25% will have the recessive phenotype. So in 10.5, this will be plants, red versus green. In 10.6, this will also be plants with the chlorophyll gene or without, which is an albino plant. And then 10.7 is looking at corn, black corn seeds versus yellow corn seeds. So you're going to be counting these, and then you're going to use your expected values to determine how close you are to the expected 75%, 25% split. Now for the last 2 experiments, things are going to get a little bit more complicated. These are not monohybrid crosses, but they will be dihybrid crosses. So 10.8 and 10.9 will both be dihybrid. Now remember, earlier we talked about the dihybrid crosses. These are 9-to-3 to 3-to-1 ratios. So your smooth data here, the expected will be 9/16 of your total. The green smooth will be 3/16 of your total. Yellow will also be 3/16, and then green and wrinkled will be 1/16 of your total of 556 of our plants. So then you should be able to add that up, and that will also give you 556. Those should be equal. Then you're going to do the math across and add up to figure out your calculated chi-square, which you will compare to your table. And then the last one, it's the fun one to count, 10.9, you're actually going to be counting these. So in 10.8, we give you the data. 10.9, you're going to count. But it's the same ratio. It's the 9-to-3 to 3-to-1 ratio, where your expected and total should, again, be the observed and expected total should be the same. And your chi-square value you will compare to your chi-square table to determine if what you're looking at is actually a 9-to-3 to 3-to-1 ratio. Is our hypothesis correct?